Now we're going to explore the principles of aerodynamics, and we're really going to get pretty deep into this. This will enable us to understand not only bicycles, but also airplanes and ships and lots of common everyday things that we observe as we go through life. It's important to understand aerodynamics to understand why it is that certain bicycles are fast and others are not. Even if you're not a cyclist, you'll find this part of the DVD very interesting. We're going to look at air resistance now. Air resistance is in the form of aerodynamic drag resistance. Now, if we explore how we can ride fast, we can lose weight, get faster wheels, lighter bike, better tires, ceramic bearings, and so on. You can take a look at that laundry list. Of those, the most important one overwhelmingly is to learn how to reduce aerodynamic drag. That's the 800-pound gorilla in the room, if you want to think about it that way. You cannot ignore it. Here's why. If I look at the power to overcome aerodynamic drag and rolling resistance and friction and bumps, we see that there's a difference. If I look at just the last three, the power to overcome the rolling resistance, friction, and bump resistance, we find that the power to overcome those is proportional to velocity raised to the first power, or just velocity. In other words, I have a one-to-one relationship. If I go 50% faster on my bike, I have to expend 50% more power to overcome those three forms of resistance. Now, aerodynamic drag is quite another animal. In the case of aerodynamic drag, the power to overcome aerodynamic drag is proportional to the velocity cubed. That makes an enormous difference when you're starting to go fast. It becomes increasingly difficult because the power needed to overcome aerodynamic drag goes up very sharply. Let's look at the power needed to increase my speed from 18 miles an hour to 36 miles an hour, so I'm doubling my speed. In the case of the force of rolling resistance, friction, and bump, in order to overcome those, I have to put out twice as much power. 2 to the first power is 2. In the case of air resistance, however, then the power to overcome that increases by 2 cubed, or 8. So my problem becomes overwhelmingly, as I go faster, a problem of overcoming aerodynamic drag. This gets us into a subject of fluid dynamics, which is a detailed exploration of everything concerning aerodynamics. Fluid dynamics is a field of engineering that looks at the properties of fluids and how it is they pass around and through objects. Now, liquids are obviously fluids, but so are gases. Air is a fluid. And wind tunnels are used extensively to study aerodynamic properties of things like airplanes, cars, trains, but also bicycles. There's a wind tunnel in San Diego, the San Diego low-speed wind tunnel, that operates at a typical wind speed that bicycles are exposed to. So it turns out that most of the aerodynamic drag testing that's done in a wind tunnel is done in San Diego at the low-speed wind tunnel. And everything associated with bicycles has been to the San Diego tunnel. The bicycles, the riders themselves, and their positioning on the bike, clothing, helmets, wheels, spokes, shoes, tires, and more. Fluid dynamics helps us explain a lot of interesting things. Why an airplane generates lift, a curveball, why two ships sailing too closely together collide, fast bicycles, tandems, and drafting. We'll actually look at some depth into some of these. There are two kinds of pressure. That's actually a third one, thinking, there's too much pressure on my job, I can't stand this, I better go for a bike ride. I'm really talking about two other kinds of pressure. This is static pressure. This is ambient atmospheric pressure. What you would experience, let's say, at sea level, where you typically would have 1 atmosphere of pressure, also measured in 760 millimeters of mercury, or 29.92 inches of mercury, or 14.7 pounds per square inch, or that last number in pascals. Those are all measurements of representing 1 atmosphere of pressure. What you see on the right is, of course, a barometer. When the barometric pressure is low, we experience stormy weather. When it's high, we experience sunny, fair weather. The other type of pressure is dynamic pressure. Dynamic pressure involves movement and air, pushing air out of the way. And we're going to look at some graphs that will help illustrate what our problem is here. This is a graph that's going to explore the relationship between aerodynamic drag and the power to overcome it. The axis down here is miles per hour, and up here is watts. Now, let's say I'm riding at 30 miles an hour. We'll look at two situations. The first graph here, the first line on the graph, represents a rider riding a road bike with his hands on the brake hoods. And the one below it is a time trial bike where we have aero bars, a skin suit, aero wheels, the whole shooting match. And at 30 miles an hour, the rider on the time trial bike has to expend 300 watts of power to overcome aerodynamic drag on the time trial bike at 30 miles an hour. The person on the road bike, on the other hand, has to expend 450 watts to maintain the same speed in a less aerodynamic position on a road bike. Most people think that dry air is less dense than humid air. That is, that humid air is more dense. Actually, it's not. At standard temperature and pressure, the density of dry air, where we have 0% humidity, is 1.2 kilograms per cubic meter. The density of moist air at 100% humidity is 1.19 kilograms per cubic meter. So humid air is actually about 1% less dense than dry air. This comes out of the gas laws of chemistry and physics if you're interested in looking up why that is the case. So you actually can ride faster in humid air, theoretically. There are two ways to reduce aerodynamic drag that we're going to look at in some depth. One is to reduce the frontal area of the rider and the bike. You see here that the rider is pushing a mass of air out of him as he's riding along on the bike. Now, if I can reduce the frontal area, then I can reduce the force of the air pushing against me. This is a friend of mine, Tom Bailey. He's a USA Cycling certified coach in Northern Virginia. And here we see Tom in 5 positions on his bike. On the left, we see Tom standing up on his pedals in a very unaerodynamic position. As we move forward, he becomes more aerodynamic. Here he is sitting down, but with his hands on the tops of the bars. Here he's sitting down with his hands on the brake hoods. Here he's in the drops, and here he's in an aerodynamic position, fully crouched over. Obviously, we see a steady decrease in the frontal area of Tom. This is why it's better as a cyclist to have a lean upper body. You want to have a small frontal area. A person with big bulbous muscles like this will have a larger frontal area, as well as weighing more. His aerodynamic drag will be larger. The other way we can reduce aerodynamic drag is to improve airflow around objects. And here we're going to look at the shapes of objects. These objects that we see here are called bluff objects. That's probably a term you're unfamiliar with. Bluff objects in aerodynamics are objects that are irregularly shaped. They're things like cubes and cylinders and squares and so on. Examples of bluff objects are all around us, actually, with bicycles. We as riders are bluff objects. So is all the round frame tubing. So are the round spokes, handlebars, helmets, shoes, loose clothing, and fenders if we have them. Those are all bluff objects. This is what happens when air tries to flow around a bluff object. We do not get a smooth airflow. The air actually separates from the object because it's not able to flow around the sharp corners. And we get behind the object a wake of unstable air. These are sometimes called eddy currents or low pressure areas that represent partial vacuums. Bluff objects have large dynamic pressure drag from onrushing air. This is the top view of the bluff object that's shown above. Streamline objects, on the other hand, are different. With streamline objects, we do not have irregular shapes. The air is able to pass more easily. We have less separation of the air from the object, fewer eddy currents, and fewer energy-sapping wakes. Here we see a typical airfoil. Now, if I look at an airfoil and I look at the stream of air that it tries to go around it, here the air is coming from the left and moving toward the right. We're going to look at and see what happens with different layers of air as the air passes over the streamline object. Immediately on the surface of the streamlined object is a very, very thin, extremely thin boundary layer. The air on the boundary layer is actually stationary. But as soon as I move away from the boundary layer into layers that are slightly further out, in subsequent layers, I start to see an increasingly free flow of the air parallel to the surface. From here to here to here to here, notice that the arrow gets bigger because the flow is increasing as I get further away from the surface. And this generates what we call a flow gradient. Actually, on the surface of the object, at the very point of it is a point that's called the stagnation point, and that's where the air actually comes to a dead stop. Daniel Bernoulli is a Swiss mathematician and scientist who lived in the 18th century, and Bernoulli made major contributions to fluid dynamics. Bernoulli was interested in viscosity and how easily fluids can flow around an object. Now, molasses is something that would be a good example of a high viscosity liquid. Water and air are relatively low viscosity liquids. Now, here's what Bernoulli found, that for a low viscosity fluid, as the fluid speed increases as it passes over an object, the sideward pressure exerted by the fluid goes down. This is sometimes known as normal pressure. I have normal in quotes because it really means perpendicular pressure. Now, if we look at that airfoil wing in that diagram there, the air has to flow a greater distance to get over the top of the wing than it does the bottom because of the shape of the wing. So the air over the top is faster than the air under the wing that travels a shorter distance. Because of that and Bernoulli's principle, the air exerted downward on the wing by the faster moving air on the top is less than the pressure exerted upward by the slower moving air underneath the wing. To some extent, those two cancel each other out, but we see that we have a net upward force on the wing, and that's what gives an airplane lift. We can see the same kind of thing here in water flowing through a pipe. Let's say it's going from left to right. On the left, we have a nice wide pipe, so the water is flowing slowly through the pipe, and it exerts a high side pressure on the side tube shown there. As I get into the middle section, the velocity of the water has to increase because the amount of space it has to go through is smaller, and the sideward pressure decreases. Over here I have high pressure. In the case of two ships, we see two ships here sailing toward us, toward the lower left-hand corner of the picture, and this represents, with those two arrows, the speed of the water passing on the outside of the ships. A bigger arrow is the water passing between the ships. Because of the shape of the ships, the water has to narrow down through a narrow channel and has to flow faster between the ships than it can flow on the outside of the ships. And what that means is I get, in both cases, a force that is pushing each ship toward the other one. And in naval operations, this is a very frequent event in a surface Navy where one ship will be resupplied by another, maybe a couple times every week. And the helmsmen that are steering these ships have to be very careful to make sure the ships don't get too close together, because beyond a certain point, they will collide and there's no way of stopping it. Bernoulli's principle also explains curveballs in baseball. We see here a right-handed pitcher. When he throws the ball curves to his left and away from a right-handed batter. Here we have a left-handed pitcher, and his ball is going to curve to the right and away from a left-handed batter. I leave it to you to figure that out, but it's a very real thing. Curveballs are because of Bernoulli's principle. And here's another one, a real mundane situation. Have you ever noticed that when you're taking a shower and you turn the water on, the shower curtain moves inward? It is simply because the speed of the air inside the shower, the air is moving along with the stream of water coming from the top of the shower. So the speed of air inside the shower is greater than the speed of air outside the shower curtain, and that pushes the shower curtain inward. Along the way of my doing the research to study this video, I met this man here, David Gordon Wilson, who is a PhD and a professor of mechanical engineering at MIT, and it will come as no surprise that he's a pretty smart guy. Dave wrote that book that you see on the left, Bicycling Science. I have that book, and I've read it many times. It's about 400 and some pages. It's very thick. It's certainly not a novel. It's chock full of really useful information, though, so I encourage you to take a look at that book. Pick up a copy of that book and read it over slowly many times, and you'll learn a great deal. I took some information from that book, and Dave was kind enough to review my video and make sure that everything I said from an engineering standpoint was correct. Now, from that book, from Bicycling Science, I extracted a few images. In the first one here, we see the air striking an object, and the air begins to flow around the object. In the second picture, we have a streamline object. Notice that the air is able to smoothly follow the surface of the object. In the third one, we have a bluff object, however, something that's round. In the case of the bluff object, we don't get a nice smooth airflow. The air actually detaches at the top of the circle. And when it does, there we get that partial vacuum and eddy currents trailing behind the spoke. So the spoke is not, or whatever it is that's round, is not very aerodynamic compared to the streamlined object above it. Interestingly, with a streamlined object, we get what's called return energy. If you look and see the angle at which the air passes over the trailing edge of the streamlined object, the angle of the arrow actually pushes the object slightly forward. So we get a little bit of what's called return energy on the trailing edge of an aerodynamic surface. These aerodynamic charts here will give us some pictures of spokes. The top one being an oval spoke. And here we see a pretty aerodynamic picture. We see a small wake of about 1/2 millimeter trailing behind the spoke, about 1/2 millimeter of unstable turbulent wake. These, by the way, are Sapim C X-ray spokes, one of my favorite spokes. Some people will tell you that it's pronounced Sapim or Sapim, but I know the name of the guy that owns the company, and I've been to his factory in Belgium, and he pronounces it Sapim, so that's good enough for me. Here we see a bladed spoke. Notice that a bladed spoke is technically a little different from an oval spoke, because in the case of the bladed spoke, the sides are parallel. And that makes a difference in the aerodynamic drag. So with a bladed spoke, we see a wider wake than we have with that Sapim C X-ray spoke right above it. A standard spoke, the last one, is far worse than either of the top two. So that's a good reason why we see that round spokes are not very aerodynamic, because they leave a large trailing wake of unstable air behind them. Aerodynamic fairings are objects that reduce aerodynamic drag. Now, fairings are all around us, but we probably don't know them for what we're seeing, but they're there. This is a picture of a mirror from a 1957 Chevy. It's not easy to find a non-aerodynamic mirror like that, because all car mirrors now look like this. All of them have a fairing in front of them to improve the flow of air over the mirror. Many of you probably have noticed this on the top of a truck. That fiberglass contraption that's bolted to the top of the cab is really an aerodynamic fairing. The whole purpose of it is to help the cab, and by the fairing attached to the top, direct airflow over the top of the trailer behind, so it doesn't hit smack dab on the flat surface. This is a picture here of a recumbent bike, and this is a recumbent bike with a fairing on it. The fairing is a lot faster than the bike without the fairing. Aerodynamic benefits of fairings are pretty easy to see when we start looking at some diagrams of wake turbulence. With a flat plate here, we have a huge wide wake of flight turbulence, not surprisingly. With something that's round, and there's the wake turbulence. With a round cylinder, we see wake turbulence also. It's not as bad as the flat plate, but it's not good. Now, in this picture here, we have a round object or cylinder, but we've attached to the back of it a trailing edge. And notice how the trailing edge has caused the wake turbulence to be reduced quite a bit. In this last object, I have a cylinder with a leading edge fairing and a trailing edge fairing. That starts looking more like a wing or an airfoil, and the aerodynamic drag is greatly reduced, and you see very little or no wake turbulence because of the fairings. If you look at Dave Wilson's book, you'll see a table that looks like this, where there are all kinds of different shapes that have been studied, and the drag coefficients, that is the extent to which they generate aerodynamic drag, are shown there in the columns to the right of the objects. I've extracted a few of those. These are drag coefficients of some of those objects: a circular cylinder, a half-closed cylinder, a flat plate, and a square, and so on. And if you notice over on the right, you see the drag coefficients. We're going to look at the drag coefficient and the results of using a fairing of a half-closed cylinder and compare that to a flat plate, which has a much higher drag coefficient. These are the two just by themselves. Half-closed cylinder, drag coefficient 1.16, and right under it, the flat plate of 1.98. Now, here is a rider with a nice flat stomach. And that nice flat stomach then looks like that, and that 1.98 is the drag coefficient from the flat stomach. Now here's a rider with a rounder stomach, a fatter stomach, but if we look at that rider, what you see when you look at that person is a fat rider. What I see is a rider with a nice big aerodynamic fairing sticking out in front of him. Now what this proves is that the guy on the left is less aero than the guy on the right, and therefore fat is faster. This proves scientifically that the fatter you get, the more aerodynamic you become, and the faster you therefore ride. Now you have to figure out if I really mean that or not. There are two ways to reduce aerodynamic drag, as we saw: reduce the frontal area and improve airflow around objects. Interestingly, these two actually work together in some interesting ways. For example, here is Tom again in 4 different positions. We're going to build a little table showing the rider, the bike and the rider, the drag coefficient on the frontal area, which will have come from that table we saw a minute ago, and then the frontal area in square meters. We're going to take those two and multiply them together, the CD and the meters, and we get the CDA, the product of the drag coefficient and the frontal area. That's also going to be measured in square meters. And then we're going to look at the power to overcome drag for each of those positions at a speed of 22 miles per hour, and that will be expressed in watts. 22 miles per hour is also 10 meters per second. Sometimes you see speed expressed in meters per second instead of miles per hour or kilometers per hour. In the first case, here's Tom in an upright position. He has a drag coefficient of 1.15, a frontal area of 0.55 square meters, a product of 0.63, and it's going to take him in that position 345 watts of power to overcome aerodynamic drag at 22 miles an hour. Now, if we move Tom into the road bike on the bars, if he gets in the bars instead of standing up, then we find that Tom has a better frontal area coefficient, as well as a smaller frontal area, a smaller product of the two, and it will only take Tom in that position 220 watts to overcome aerodynamic drag at 22 miles per hour. Over here, Tom moves into his drops, and in that position, he has a more aerodynamic position, a smaller drag coefficient, a smaller frontal area, and a smaller CDA product of the two. And once again, the power to maintain 22 miles an hour continues to go down. If we extrapolate from that into what it would look like with Tom on aero bars, we see that all the way over on the right, his power goes down dramatically. Now, it's not so important that these numbers be absolutely precise for every situation, as much as to see the trend here, that as we go from upright and unaerodynamic to more and more aerodynamic, we get a decrease in the frontal area, but also a decrease in the drag coefficient. The product of the two makes our power go down quite sharply. It's for this reason that when you see people riding in groups, they often draft in a pace line or a drag line to reduce drag. If you're not really sure about the truth of that, if you look at the Discovery Channel and look up, you'll find that Mythbusters did a little study one time, and they actually proved to themselves that the reduction of drag by drafting is real. You already know that, but it's kind of an interesting study that was done by Mythbusters anyway. Now I'm going to look here at some cyclists that are riding. In this case here, cyclist number 1 is riding toward your left, and the wind is coming toward him. Now we're going to study carefully what happens here. Now here we have the airflow attached to the rider, and here the flow separates because the rider is a bluff object. And as the flow separates, we get these high energy wake of eddy current that we have come to understand. That's rider 1. Back here is rider 2. Since rider 2 is so far behind rider 1, rider 2's aerodynamic profile will look exactly like rider number 1's, equally as bad. Now as rider 2 gets closer to rider 1, at some point rider 2 will get into the slipstream of rider 1. And now you see quite a difference, because now rider 1's slipstream has effectively been extended past rider 2, so there's no drag behind rider 1 at this point. It's for this reason that drafting is faster. It's even faster if the two riders take turns. Rider 1 is in front, and then rider 2 is behind, and they take turns. Each rider is faster that way, and they both save energy. This graph here is going to show us a little bit more about that phenomenon. So here we have two riders riding toward your left in the direction shown by that arrow, with the wind coming toward them from the left. P is the puller. He's the person who's out in front of the drafter, and this line here represents the diameter of the puller. Think of that as sort of an average of the shape, the diameter of the rider with part of his bike. And behind him is the drafter. Now, an interesting thing happens when the drafter gets to 2 diameters distance behind the puller. What happens there is, if we look at the drag on the drafter goes down by quite a bit. It reaches a minimum, as we see there, at that point of 2 diameters. But up here on the drag of the puller's drag also goes down at that point. That's quite a surprise. And the combined drag goes down as well. So we see actually that the wheel sucker helps. To the extent that you are riding along and you have somebody that comes up and drafts behind you, it actually does reduce your drag a little bit also. It makes you faster, even if that drafter never volunteers to get out in front and pull you. And this is one of the reasons that tandems are so fast, is because of this fixed ideal aerodynamic position. It doesn't hurt that tandems often have a good weight ratio also of the rider to the bike, but it's also mainly for aerodynamics that we get this increased speed, because we have a stoker in the back and a captain in the front, and the captain is always in a perfect aerodynamic position relative to the stoker. This is a couple of friends of mine that live in Florida, Bob and Rose Jordan, riding their tandem. So they're in a perfect aerodynamic position here. And here's Rose, who is the captain and the puller on the front. And here's Bob, who's the stoker on the back. Unfortunately, Bob isn't really working. He's just sandbagging and reading a book. Happens to be the Big Blue Book of Bicycle Repair, published by my friend Calvin Jones of the Park Tool Company. It's interesting to contemplate whether spokes could draft on each other or not, since there are many spokes in the wheel. It's plausible that they could, but experimentally it's been determined that they're way too far apart. So each spoke, as the wheel is turning, has to act on its own to cut through the air and deal with its own aerodynamic problems. We're going to look here at some zip carbon rims, starting from left going to the right. The one on the left is the Zip 303. That is the shallowest of the Zip family. And then we have the 404 and the 808, the 1080, and all the way on the right, a disc wheel. Obviously, the depth of the carbon in the carbon rim increases as we go from the left to the right. Let's see what the consequence of that is. This has been extensively tested in a wind tunnel. And the testing was done by Fabian Cancellara. That's not actually Fabian in that picture, but he did the testing. And this is the protocol that he ran. He rode a bike at 30 miles an hour at a constant power of 300 watts at a distance of 40 kilometers. This was done in the San Diego low-speed wind tunnel. And he tried this with all different kinds of zip rims. The first one was an aluminum rim, a clincher rim. These are all clinchers with a depth of 20 millimeters and a weight of 425 grams. Whatever that amount of time was, that established a baseline for subsequent comparisons with carbon rims. In the case of the Zip 303, the depth is 45 millimeters. Notice that the weight of the 303 is higher, it's greater than the aluminum rim, but Fabian Cancellara was able to ride the time trial in 1 minute less time. In the case of the 404, we go to a deeper section rim. The rim is still heavier, but the time goes down. And with the 808, the same trend continues. In 81 millimeter deep rim, even heavier rim, but even faster. And here, the 1080, the deepest of them all, 108 millimeters, 800 grams, almost twice the weight of the aluminum rim, but Cancellara completed the protocol time trial in 1.5 minutes of less time. Now, the only conclusion you can reach from that is that the aerodynamic advantage of these deeper section rims outweighs the weight disadvantage. And it's because of the streamlined flow of air over the streamlined shape of the carbon rim that is the case. There's a lot less drag over the deeper section rims than there is over the shorter section rims. There's also shorter spokes, which helps. Somewhat surprising in this whole study is the fact that if you slightly roughen the surface of an aerodynamic surface, you actually make it faster. You reduce the drag slightly. When you roughen the surface just a tiny amount, it makes the next layers able to pass more easily, and that makes the flow better. You see that with something as mundane as golf balls. On the type as a round sphere golf balls, which is what golfers at one time used. But if you look at the trailing wake, you see a large trailing wake of aerodynamic turbulent air behind the spherical smooth golf ball. On the other hand, if you put dimples on it, the dimples serve as a slight roughening of the surface, and the dimples make the golf ball more aerodynamic and reduce the size of the trailing wake, so the golf ball flies further. In the case of dimpled rims, as we see, we get less drag. It's interesting to contemplate, as Zip has done, different shapes of dimples. Dimples could be circles, they could be hexagons, they could be whatever, but there are manufacturing considerations that come into play. You have to be able to manufacture the rim, and the circular dimple is what Zip has settled on, at least for the time being. I made a number of sets of wheels with Envy rims. These are very high quality carbon fiber rims, 45 millimeter of depth, and these are the weights of the rims. A 45 millimeter Envy clincher is 440 grams, which is pretty light for a deep section carbon rim, and the tubular is even lighter. These are very sturdy rims. I can put a lot of tension on them, so I like that. I made a set of wheels for a customer not too long ago that came in at an incredible 1,100 grams for the wheel set. This was using Envy tubular rims, DT Swiss 190 hubs, Supreme CX-ray oval spokes, and internal aluminum nipples, and the guy loves the wheels. Now, one caveat emptor, one caution in this whole thing, and it's this: beware of lookalikes. Beware of rims from a guy named, they'll call him Will Cheatham. Now, you can look on the internet and you can find cheap rims, and they may look good. They may come from some other country. They may not have any labels on them. You think, well, that looks like a pretty good rim to me. You really don't know what you're getting, though. And the reason is, if you buy rims from manufacturers like Zip, Bontrager, Envy, Reynolds, Easton, reputable companies like that, they are staffed with skilled scientists and engineers. I know some of them, and these are really smart folks, I'm telling you. And these are rims that are made to very high standards, and they're extensively tested in the wind tunnel, so you know that you're getting something that's going to be aerodynamic like you expect. But otherwise, you don't, because subtle changes can affect the aerodynamic properties quite a bit. It turns out that this is a very complicated subject, not surprisingly. A rotating wheel is a complex thing to study because the wheel is spinning at the same time that it's moving forward. Shown here is a Trek Speed Concept bike with ALS D3 wheels. We'll see that bike again in a couple of minutes. But some very high math is used to solve some of the mathematical problems associated with the aerodynamic drag on those kinds of wheels. This is not Math 101. This is very complicated stuff, complicated differential equations that are extremely complex and require millions of calculations to solve some problems. And this is done using computational fluid dynamics. Computational fluid dynamics, or CFD, is mathematical modeling that studies subtle changes in the contours of aerodynamic objects. And because of all that complicated math, as I said, there are complicated equations, and we have to use very powerful computers to solve those. But there is a great deal of research and development that is done using computational fluid dynamics. Here's an application where computational fluid dynamics could be useful. Let's say I come up with 5 theoretical concepts for a carbon fiber rim. I could make A, I could make B, C, D, and E, and I think, they all look pretty good on paper. But I do my modeling using computational fluid dynamics, and by doing that computer modeling, I can pick out 2 out of those 5 that look like they're the most promising. Let's say it's B and E. And then I can make prototypes. Prototypes are very expensive to make. If I can make prototypes of the most promising candidates, that's a lot cheaper than making prototypes of all 5. So I make expensive prototypes, and I take them to the wind tunnel. That's also very expensive. Aerodynamics is not the same thing as being stable. Something can be very aerodynamic and be unstable. So design here is important. It's a design imperative to make wheels that are stable. And we're going to look at some factors that bear on that issue. One is yaw angle, one is air currents on the rim surface, one is vortex shedding, and one is stability at high speed. Yaw angle is something that comes out of airplane terminology. Let's say I'm flying in an airplane, I'm flying due east from Chicago to New York, and my course is, let's say, 90 degrees due east. Now, if I have no headwind, my airplane speed is, let's say, 300 miles per hour. But in fact, in this scenario here, I have a side wind coming from the east-northeast at 80 degrees, which is at, let's say, 50 miles an hour. And if I run that calculation out, that gives a yaw angle of 1.6 degrees to the left. The consequence of that yaw angle is I have a heading which is slightly left. Instead of 90 degrees is 88.4, and that slows me down. My course velocity, instead of being 300 miles an hour, is now going to take me longer. On a bicycle, yaw angle is a little bit of a different animal. Let's say I'm riding on this road here, away from the camera, and I'm riding straight in a no-wind condition, and I'm riding at 30 miles an hour. Here I have a change. I have a side wind. I have a side wind coming directly from the right at 20 miles an hour. At 20 miles an hour, that side wind, what that's going to do is it's going to reduce my speed. I have to keep the same straight heading, because if I head into the side wind like I would do with an airplane and with a bicycle, I'll just ride off the road. So I have to keep my bike pointed straight down the road, notwithstanding that side wind. But what I have to do is I have to lean into the wind. So I point the wheels down the road, but I lean into the wind, and that leaning offsets the wind. But what happens is when I lean, the wheels want to slide to the left. And what stops the wheels from sliding to the left is the increased friction. And that increased friction that I have between the tire and the road when I'm leaning into the wind is more than the lower rate of friction when I don't have to lean into the end. And that increased friction is what slows me down. So even though the side wind is coming straight at me from the side, it still slows me down. Now, yaw angle, interestingly, decreases with speed. I'll walk you through this diagram here. We see here a blue arrow indicating side wind speed, and that line represents a side wind of 5 miles an hour. And my example there says if you ride at 20 miles an hour in a 5 mile an hour side wind, your effective yaw angle is 14 degrees. So if I'm riding 20 miles an hour and 5 mile an hour side wind, I go from 20 up to that point and go left when I hit the line, and I get a yaw angle of 14 degrees. On the other hand, if I increase my speed to, let's say, 30 miles an hour, I'm still at 5 mile an hour side wind, the same amount of side wind, but my yaw angle, according to this graph, will reduce now from 14 degrees to about 9. And it's for this reason that high-performance rims are designed for faster riders to work at the best efficiency at yaw angles of plus or minus 15 degrees, because fast riders, professional riders, and very high-end skilled non-professionals are going to ride fast enough that the yaw angle, the effective yaw angle, is going to be in most cases less than 15 degrees. Computer images of a moving wheel are something interesting to look at. At the bottom you see some computer images of the ZIP 404, the ZIP 808, and the ZIP 1080 rim. As we said, a moving wheel has translational and rotational kinetic energy, so it's a very complex picture. And what happens is that air molecules briefly accumulate on the rim surface. And we see that rim surface accumulation in the form of recirculating currents, which is what you see there in the picture, those swirling figures. And they occur on both sides of the wheel. I get this recirculation current on both the left and the right side of the wheel. And this creates regions of unstable air. And those unstable air regions are shed as vortices. Let me explain that with another diagram. Here we're looking at the top view of a front wheel, which is turning in the direction shown, and the bicycle is moving, let's say, up the screen. Let's see what it looks like. We have molecule accumulation on the rim in the form of recirculating patterns. It's on the rim, and at this point in time, let's say that the pressure is equal. I have equal amounts of recirculating patterns. This is before anything sheds. Now what happens is the vortex sheds on the right side of the rim. As the vortex sheds on the right side of the rim, we get a partial vacuum on the right side of the rim, and that creates unequal pressures, and the wheel wants to turn to the right. Now a minute later, we see a similar situation. Equal pressures on both sides, the same amount of vortex, same recirculation patterns on both sides, but this time the vortex on the left sheds, and once again we get a partial vacuum on the left, unequal pressures, and the wheel wants to turn to the left. This periodic loading and shedding of air recirculation currents is what leads to buffeting. If your bike is buffeting, it's probably not because the wheels are out of true. It's probably not because there's something misaligned in the frame. It's because of this buffeting that occurs on the rim. This is particularly critical when we're looking at time trial bikes and triathlon bikes. These are bicycles that are not easily maneuverable in the first place. The rider's weight is over the front wheel, and the rider wants to spend all of his or her energy controlling the bike. All right, this is Dimitri, and Dimitri is going to demonstrate on this $10,000 high-end time trial bike. Go ahead and pedal, and I'll explain what's going on. Now, notice that Dimitri is on these aero bars. Normally, when you be riding a bike, you'll be out here with your hands out here. When you go from here to here, your whole body becomes a lot narrower from an aerodynamic standpoint, but you lose a great deal of lateral stability also. So it's a very squirrely feeling at first to go from riding on regular handlebars to riding on these aero bars. Notice also his body is positioned forward and he's over the front wheel. Now this is a bicycle that is meant to go really fast in a straight line. What Dimitri wants to do to win a time trial is to not have to worry about his bike. He doesn't want to worry about his bike. He doesn't have to think about anything except keeping his head down and going as fast as he possibly can with the right amount of power. He doesn't need to be worrying about controlling the bike because of instability in the front wheel. So when you start with a bike like this, if you get this buffeting in the front wheel, because of what I described in the DVD a minute ago, then the rider starts worrying about the bicycle. Instead of just pointing straight ahead and riding as fast as possible, when you start worrying about your bicycle, you don't ride as fast, you start becoming tentative. So it's really important to have a wheel that is designed to be as aerodynamic as possible, but also as stable as possible, and eliminate as much as possible that side-to-side buffeting. That's our next topic, ways of reducing that amount of buffeting. So the goal here is to keep the vortex buildup to a minimum by having frequent shedding of small vortices. That's going to create minimal buffeting. Less buffeting means more stability in the ride and a faster rider. Subtle changes affect the vortex shedding, and this brings us back once again to the necessary engineering and testing behind the product. I'm going to take you through a little bit of evolution of the shape of carbon rims, starting on the left with the traditional V-shaped rim, and then going to the right after that, the 404 clincher with a hybrid toroidal profile, and then more recently the Zip 404 carbon clinchers. The one on the left is the Firecrest clincher, and the one on the right there, the 404 Firecrest tubular. Here we show the same shape rims, and I've just photoshopped a little tire onto the rim. Now in this picture here, what we're looking at is the front wheel of a bicycle, and the bike is moving from left to right in the direction shown, and the wheel is rotating forward as you can see by the arrow. This is what the wind sees. So if I'm going from left to right, the wind is coming from right to left, as we show it there by the arrow. What the wind has to do is figure out a way to get around the wheel. The first obstacle is the tire on the front of the wheel. After it gets around the tire, then the wind has to get around the rim. As it goes to the other side of the wheel, the wind has to get around the rim, and then it has to get around the tire. Now this is the same picture. If we look at the top one is the V-shape, then the toroidal rim setup, and here we have the same picture that the wind sees looking at a Firecrest rim, and then another Firecrest rim, the top one being the clincher and the bottom one being the tubular. These are the 404 Firecrest rims, newly out from Zip, and these give us improved behavior in crosswinds, less steering correction required, and also we're able to maintain better aerodynamic features at higher yaw angles. Once again, this is the Firecrest rim, and I made these little diagrams under it to show you that basically what we're seeing here is a plane of symmetry. If we just take a look at that little picture on the right, the part of the rim that has the tire on it, followed by just to the left of the plane of symmetry is the rest of the rim. Notice how the right side of the tire rim combination is a mirror image of the other side. And then when you get to the back of the wheel, you once again have that same plane of symmetry. This seems to minimize the amount of aerodynamic drag looking at the wheel as a whole. Bontrager has also done some great things with aerodynamics to improve their wheel. This is the Bontrager ALS D3 wheel. D3 stands for dual directional design. Once again, we see the wind coming from the right, and the same kind of benefit here as we got from the previous examples. Outstanding results from their R&D effort, and these are very nice wheels, low weight, good climbing wheels, optimal handling with higher yaw angles, and once again, these also are available in tubular or clincher. The ultimate for speed in a bike is a time trial bike. Time trials are sometimes called a race of truth because all you have is a clock that you're racing against, and you have no teammates to help you out. They're short and fast. Your goal here is to reduce drag with the bike, the helmet, the clothing, the wheels, and the rider position. Everything is optimized to make the time trial bike and rider as fast as can possibly be made. This is the Trek
speed concept bike. We'll look a little bit later on again at this bike and how this can be used for both time trials and triathlons. Of course, you want to have the right hat for the occasion, one of these weird looking hats that tapers in the back. And if everything else is going for you, then you want to have a skin suit, because the skin suit actually will reduce drag from the skin, similar to the kind of suits you see swimmers using in a tank when they're racing in swim meets. This is a suit from Louis Garneau.